Okay, I'll get started. I hope you can hear me. I was just going to start with a couple of announcements that I wrote down here. One is important one, of course, that starting this week with lecture quizzes, with homework assignments, they're counting for credit. So we'll have a lecture quiz today that will count for credit, and your recitation problem that you submit in Canvas and your homework answers that you submit in WebAssign on this coming Wednesday, that account for credit too. So if you have any questions on that, let me know. You can let me know through the chat. The other thing I wanted to mention is, so this class works off a bundle involving the textbook and the WebAssign in registration. And certainly the cheapest way to get that was through the purchase of the bundle of the hard copy textbook with WebAssign or the ebook with WebAssign. If somehow you purchase those things separately, you could let me know and I'll pass that along to a rep, a textbook rep, because I think they would work with you so that you weren't overpaying by inadvertently buying those two things separate. So if that happened to you, just feel free to let me know. Just looking for any questions? No. So then maybe I'll start. I'll share my screen, my slides. And let me grab my annotation on my drawing pad here. And then I'll get started. Okay. So last class, we introduced the description of motion. So last class was really about this language of displacement and velocity and acceleration. We looked at equations for displacement, velocity, acceleration. We looked at graphs describing displacement, velocity, and acceleration. And we also tried to illustrate them with some examples. Today's class, we're going to apply that language for describing motion. We're going to talk about a specific, a very important case, that's falling bodies or falling objects, which are an example, the classic example of constant acceleration motion. And then we're going to talk about some other examples of constant acceleration motion and the equations of constant acceleration motion. So that's the plan for today. So as I hinted, today's class, this is why Lady Gaga is here. Today's class really features this momentous event in physics, this huge breakthrough in physics due to Galileo. And it was a breakthrough in the sort of understanding of falling bodies. It was a breakthrough in the understanding of gravity. And it actually led to ultimately this kind of joining together or this unification of what we call terrestrial motion. That's motion of everyday objects like basketballs and footballs on Earth, and celestial motion. That's motion of the moon around the Earth or the Earth around the sun, etc. But joined together our understanding, description of those two types of motion. So it's in this one class, we meet this incredible discovery that really changed physics. I mean, I don't want to oversell the class. The discovery I can oversell, but not the class. Okay, so this was a discovery made by Galileo. Yeah, I'm sure you know his name. He was an Italian mathematician, astronomer, physicist. he was around and made this discovery about falling bodies, you know, the scale of 400 years ago. It sounds like a long time, but when you think about, you know, the history of civilization, the history of, you know, of the evolution of Homo sapiens, is nothing. But, you know, on our lifetime scale, it seems like a long time ago. We think of Galileo as kind of the father of physics, and he's the father of physics in the sense that he was really the first person to do experiments, first person to make measurements, and in that way discover physical insight. And so that's why he's considered the father or grandfather or whatever of physics. Okay, so I want to talk about his work on falling bodies or falling objects. So the falling body, when we say the word falling body, or we say the word falling object, we just mean an object that's dropped, an object that's released, and that object or that body falls to the ground under the pull of gravity. And if you went back thousands of years, the Egyptians, the Greeks, the Egyptian Greek philosophers thought about motion and falling body motion. But as I say, it's really Galileo that was the first person to go beyond thinking about falling bodies and motion to doing experiments on falling bodies, making measurements of falling bodies. And you probably know, you probably heard of his famous experiments dropping this or that object off the Leaning Tower of Pisa in Italy. Well, he had a brilliant idea for studying the motion of falling bodies. Now, if I just drop an object to the floor, that object, as it drops to the floor, well, it drops so quickly, it's very hard to measure things. It would be very hard for me to measure the, you know, the speed or the acceleration of that object dropped to the floor, because that object is dropped to the floor, falls to the floor so quickly. And it would have been especially hard for Galileo 400 years ago to measure the speed of the velocity of that object dropped to the floor. What his idea was, and this is a really clever idea, kind of cute idea, is to slow down the pull of gravity on the object, on the falling object. Reduce the pull of gravity on the falling object. So instead of falling quickly, it fell slowly, and therefore he could make measurements, make accurate measurements of the motion of the falling body. And he did that by putting the falling body on a slope, or on what we typically call an incline. And so that's what you see over here on the right-hand side. His idea for studying falling bodies is to slow the fall down, to slow the pull of gravity down by working on an incline, rather than over here on the left to deal with the very fast falling motion when the body falls straight to Earth. Okay, so I want to demonstrate his experiment. And so let me try and do that. I'm going to share a different screen. So this will take me a moment.
I love his play-by-plays. I kind of talk like that too sometimes, I feel like.
I think I got to mute everybody because I can hear others. I can do that. Okay, so I'm hoping you see me or somebody that looks like me in the chemistry physics large lecture room. And I try to reproduce Galileo's experiment with the falling bodies. And like Galileo, I'm going to let an object, it's going to be this little red cart, fall towards Earth, not straight down, but along a slope, gliding along a slope. And so that's what I've got in this video. If I can point it out, here's the cart, which I'll release. Here's the slope. It's going to fall down. And it's a gradual slope, but maybe you can see, look at the support. Over here is the support on the right. Over here is the support on the left. It's a bit higher on the left. It's a bit lower on the right. So it does slope downwards. I've also marked some distances. I've imagined some units, 1 foot units. And here's from where I'm releasing the cart, the first foot. Here is from where I've released the cart, 4 feet. And here, finally, from where I release the cart is 9 feet. And we'll see those intervals of 1 foot, 4 foot, 9 foot are very important in Galileo's measurements, in Galileo's results. So let's watch this little clip. And here the object is sliding down the incline, falling down the incline. And you may notice, at least approximately, that it takes the same time interval to go to 1 foot as it is to go from 1 foot to 4 foot, as it is to go from 4 foot to 9 foot. So I think I'll just play that one more time. I mean, it took me 2 hours to make it, so I may as well play it twice. And here we go, gradually falling down the incline, traveling 1 foot, and then to the next 4 foot marker, and then to the 9 foot marker in the same little intervals between those markers. Okay, so now I'm going to go back to my slides. We've repeated, so we've all just repeated Galileo's famous experiment, which is nice. So now I want to share, if I can, his data. So I got hold of Galileo's notebook from his original experiment, 400 years old, and here's his data. And what he did and why he is the father of physics is that he not only just watched and thought about the falling body, but he made measurements of the falling body. And here's the results of his measurements. He measured the distance traveled by the falling body as a function of the elapsed time of the falling motion. And that's what you see in this little overhead here. I'm going to get back my annotation. So right here, 2-year-old handwriting coming back. After 1 second, he measured his falling body had traveled 1 meter. After 2 seconds, he measured his falling body had traveled 4 meters. After 3 seconds, he'd measured his falling body had traveled 9 meters. And after 4 seconds, it had traveled 16 meters. And so that was his data. This was his experiment. This was his data. This was a breakthrough event in physics, breakthrough event in science to actually do an experiment. Well, I'm sure you can spot a pattern. Compare the times and the distances. I mean, they're different dimensions. This is the dimension of time. This is the dimension of length. But there's a simple relationship between them. The distance traveled by the falling body is in proportion to the square of the time. Now, I just got to plug in my, I got to plug in my laptop quickly because it's telling me it's going to run out. So you got to give me 1 second here. Okay, that's better. For a moment, I thought I'd forgot my power cable. That would have been really bad, but I didn't. Okay, so back to where we are. My heart rate's now gradually decreasing. And we've spotted in Galileo's data, like Galileo spotted in his data, that there's a simple relationship between the distance traveled and the elapsed time, that the distance traveled is in proportion to the square of the elapsed time. So, you know, after 1 second, 1 meter. After 2 seconds, it's 2 squared, 4 meters. After 3 seconds, it's 3 squared, 9 meters. After 4 seconds, it's 4 squared, 16 meters. Simple pattern. The big question is, why is there that simple pattern? Why is the distance traveled in proportion to the square of the time? And so that's really what Galileo set about trying to answer. And the story goes that he slept on it, and he woke up in Pisa on this nice Italian morning, refreshed, and had an idea. Had an idea that the reason for that simple relationship between distance traveled and time elapsed was because the object was falling under gravity with a constant acceleration, what we call a uniform acceleration. And so that was his basic idea. In the relationship between distance and time, he was actually seeing this underlying constant acceleration, uniform acceleration of the falling body. So I want to show you, or I want to explain to you how that works. And so here's a sort of graphical picture of Galileo's idea that the body falls with constant acceleration. So if you look down on this graph, let me get my pen working. I plotted time for the falling body versus the acceleration of the falling body. And this is his hypothesis, that as the body falls from where it's released to where it hits the ground, it's accelerating. It's always accelerating with the same constant acceleration. So that means that an acceleration versus time graph for the falling body is just this horizontal line. This blue line represents acceleration versus time for the falling body. And so we're going to explore the consequences of that. And we're going to do that using the work we did in the last class on the description of motion, on acceleration, velocity, displacement, and how those things are related to one another. Okay, so the first step, there's going to be 2 steps here. So this is the first slide, there's going to be a second slide here. The first step is to see the consequences for velocity of a constant acceleration. And then the second step will be to see the consequences for distance traveled, displacement, due to constant acceleration. So here we're going to just look at the consequences for velocity. And the way I'm going to find the consequences for velocity is to use the relationship between velocity and acceleration. And here is that relationship, this little guy here. Now I want to get my pen again. This is a definition of velocity. No, it's a definition of acceleration. If you remember last class, we said acceleration is the change in velocity, that's a delta v, divided by the elapsed time, that's a delta t. And so that is just the definition of acceleration from the previous class. Now I'm going to apply it to the object that I dropped. And I dropped that object from rest. Galileo dropped it from rest. So if you drop it from rest, this velocity, change in velocity, is just really the velocity that it reaches, v, because it started with no velocity. And this change in time, this delta t, is just really the time if you start the clock when you release the object. And so I've replaced the delta v by v. I've replaced the delta t by t for my object starting from rest. And then I've just rearranged this equation as an equation for the velocity. So I divided it through, multiplied through by the time. And you discover that the consequence of constant acceleration over here, A, is that the velocity will increase linearly with time. And so if you have an object with constant acceleration, a hallmark of that, a signature of that, is that its velocity will change linearly with time. And for this particular case of an object starting from rest, that velocity is proportional to time. And that's what I've drawn down here on this graph. So this is now a graph of time on the horizontal axis, velocity on the vertical axis. So it's a velocity versus time graph. The blue line is showing the velocity increasing linearly with time, and it's a consequence, a signature of constant acceleration. So let's remember that and go on to the next slide, if I can. Here's the next slide. I got to clear up the junk here. Must be a way of automating this, but failed to figure it out. So now we know our constant acceleration leads to a linearly increasing velocity. Let's explore next the consequences for the displacement of the object. And to do that, I'm going to use something else from last class, which is our definition of velocity, in terms of displacement. So just like on the previous slide, we use the relationship between acceleration and velocity to find out the consequences for velocity of constant acceleration. In this slide, we're going to figure out the consequences for displacement due to linearly increasing velocity based on our definition of velocity. So here's our starting point. This was the definition of velocity. Oh, crap. Here's the definition of velocity. The average velocity is the displacement, we call that delta x, divided by the elapsed time, delta t. In this particular case, with the object starting from rest, then the delta x here in the numerator, this is really just x. It's really just the distances traveled from that starting location of where I released it. And so I rearranged the equation here for x. So this is the displacement equals the average velocity times the time interval. And the time interval, I can write it delta t, or if I imagine starting the clock at time 0, I can just think of this as average velocity times time. Now, the average velocity is not the final velocity. It's not the initial velocity. It's the velocity midway between the average and final velocity. And since we started from 0 velocity and the final velocity we're calling v, then the average velocity is half v. And so I fed in here to the equation the fact that the average velocity here is half the final velocity. Then I fed in the fact that the final velocity, based on the last slide, is equal to acceleration times time. That was the result we derived on the last slide. The velocity increases linearly with time. And so I fed in this result here. So I put in two things here. Put in the average velocity in terms of the final velocity, put in the final velocity in terms of the elapsed time. And I've made an equation. And it's an equation that relates the distance traveled, or displacement, to the elapsed time, t. And it says that if you have an object falling with constant acceleration, that causes the velocity to increase linearly, then the distance traveled, the displacement, will be in proportion to the square of the time, t squared. And that's exactly what Galileo had recorded in his experiment. And so this was a remarkable moment for Galileo. He had made measurements, made experiments, and determined that the distance traveled by a falling body was in proportion to the square of the time. Now he had hypothesized the cause for that, constant acceleration. And in this little 2-slide derivation, don't worry about, following every little detail of it, but basically by using our language of motion and how acceleration is related to velocity, velocity is related to displacement, we've shown that that constant acceleration creates a motion that involves linearly increasing velocity and a distance traveled, displacement, that grows in proportion to the square of the time. Exactly the results of Galileo's and our experiment. So it's like this magic moment in physics. Okay. Let me clear that junk. Next slide. So Galileo actually went further. I mean, those last few slides, so, great, you've measured the distance is in proportion to the square of time. Great, you've interpreted that as a constant acceleration. But this next step was really revolutionary. What he said then, what he thought then, was that that constant acceleration of an object falling towards the ground is the same for every object. Every object falls with the same constant acceleration of gravity. Now think about that for a moment. So he's saying that, for example, if you drop a feather and an elephant, feather's really light, elephant's really heavy. Galileo's saying that they experience the same acceleration of gravity. And they therefore fall to ground with the same acceleration of gravity. They fall to ground in the same length of time at the same speeds. It's a remarkable statement. It's sort of revolutionary statement that's at odds with our sort of everyday notions, our everyday experience. So it was really a revolutionary statement. So let's try and test this. So I actually have, I'm going to put the camera on now. And I'm going to take my headphones off. This is my office, by the way. Somebody asked me earlier on if it was a jail cell and I was working out of jail, but no, it's actually my office. And I'm going to try and do a demonstration in here. And I've got one heavy object, the textbook, right? It's an old copy of the textbook. And I got one light object here. It's just a sheet of paper. So I don't have a feather and an elephant, but I'm going to drop the paper and the textbook. And remember that Galileo's hypothesis is that all objects, so both these two objects, will fall to ground with the same constant acceleration. Okay. So you can't see my head, but I'm holding these two objects, and so I'm just going to drop them to ground, and I think you can see a bit of the ground. Well, it's clear that those two objects did not fall to ground with the same velocity. And they did not strike the ground at the same time. And that seems at odds with Galileo's statement that the feather and the elephant would fall to ground with the same constant acceleration, or the sheet of paper and the entire textbook would fall to ground with the same constant acceleration. So that looks like Galileo was wrong. But he wasn't wrong, he was right. So let's go back to my slides. And I'm going to show you one or two videos here of dropping different objects where we do say that they do fall under gravity with the same constant acceleration. And the reason the textbook and the sheet of paper didn't fall with the same constant acceleration is because of air. So when objects fall under gravity on Earth, they're falling through air, which is kind of like a fluid that they're moving through. We don't normally notice the air, but of course the air is there, otherwise we'd die. But the objects are falling through the air, and there's what's called air resistance. And it's not that the pull acceleration of gravity on the sheet of paper and the textbook were different. They're actually the same. It's the effects of the air resistance on the textbook and the sheet of paper that are different. And that causes them to appear to fall under gravity with different accelerations. But actually the gravitational piece, if we could strip that off, look at that on its own, it's the same. And so I'm going to show you two videos. These two videos are basically where we're going to remove the air from the room. And as I say, I couldn't remove the air from this room. It's firstly not possible, and secondly, I would die. But we can, in special cases, find a room to remove the air. So let's try and do that.
It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
Back on the side.
Exactly the same.
Feathers don't move, nothing. Look at that.
That's just brilliant.
Okay, so that's one example of a falling body. I hope you can hear me.
We can hear you.
Okay, thank you. I got really confused about sharing the sound from a video versus sharing, the sound from my microphone. I think I'll show you one more video. So that's really an amazing thing to see that feather and that bowling ball fall at exactly the same rate. And what you're seeing there is when you do remove air resistance, that falling body motion becomes so simple with gravity's pull on everything, no matter whether it's a feather or whether it's a bowling ball, is exactly the same. So we'll do one more. This one, so they did the same experiment, but when they went to the moon, they did it on the moon. They dropped a feather and a heavy object on the moon. And of course, on the moon, I'm sure that there's no air. It's vacuum. And so you get rid of the problem of air resistance. And also on the moon, I'm sure you know this too, the acceleration of gravity is much smaller. And so on the moon, you're also slowing down the fall of gravity so you can see the fall more clearly.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got
beautiful picture, Dave.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Okay, so again, it's to me, it's a fantastic demonstration of something that seems that from our everyday experience, that obviously a feather and a hammer don't drop to Earth at the same rate. But if you strip off the atmosphere, you strip away the air resistance, that actually everything is super simple. Everything falls to Earth with the same constant acceleration. Okay, so I've gone back to my overheads now, and we've done those two demonstrations. And so as a conclusion, the great simplicity about falling objects is that on Earth, on the surface of the Earth, all objects fall with the same gravitational acceleration. That gravitational acceleration is 9.8 meters per second squared. That's the numerical value. Once you do this class, you will, I think in your life, you'll be 95 years old. You won't forget 9.8. All accelerations of gravity for any object on Earth is 9.8 meters per second squared, and it's downwards, meaning it's towards the center of the Earth. So, for us, it's straight down towards the center of the Earth. If you're in Australia, it's straight down towards the center of the Earth. Well, now let's get on to the fun stuff, some equations. And I want to talk about the equations of motion. So we're going to move on to the equations of motion now. Now, I've got to get my pen going again. Well, we actually have just derived an equation of motion. We figured out distance traveled is 1/2 the acceleration times the square of the time for a falling object. And that's an example of an equation of motion. So we just figured an equation of motion. So nothing magic, mysterious really about equations of motion. They're just equations relating things like acceleration, velocity, distance, time. This one is a special case equation of motion. So the special case is that is the distance traveled versus the elapsed time for an object that is dropped from rest. Dropped from rest means that its initial velocity was 0, and that we're going to measure its displacement from that location. And the way we normally write that is that the initial velocity and the initial position, what we call x and v, we write x naught, the initial velocity was 0. V naught, the initial velocity of the falling body was 0. So that's a equation of motion, a special case equation of motion for this situation. And what I want to introduce now is 3 equations that are the general equations of motion. And these equations, these 3 equations apply to the case of constant acceleration. So they only apply when you have constant acceleration or uniform acceleration, but they don't require the object started from rest. They don't require the object started from the origin. And those equations are these 3. So here's number 1, number 2, and number 3. And these, if you look sort of broadly at these equations before we get into their guts, they're equations that relate, for example, positions or displacements, the x's you see here, to velocities, you see v naughts and v's here, to acceleration, you see a's here, and to elapsed time. So there are equations of motion that connect all those quantities that we use to describe objects moving through space and time. Now, I've actually color-coded them. If an object were to start from rest, this term here with the v naught, that would go away. And this term here with the v naught, this term would go away. And so in that case, you see that familiar example here, 1/2 at squared that we got for the falling body. Anyway, these are what we call the 3 equations of motion that we use to describe constant velocity motion. Constant acceleration motion. And the falling of objects under gravity is the classic example of constant acceleration motion. But what we're going to turn to now is kind of working on different different illustrations or different examples of using these equations of motion. Oh, and so first we're actually going to have a quiz, and then we'll get on to some examples. So let me post out the acceleration of gravity when you throw an object into the air, and then it falls back down. And there's an important story behind throwing an object into the air and when it's falling back down. So on the way up, when the object is slowing down, the acceleration of gravity is downwards, opposite the direction of motion. That's why it slows down. On the way down, the acceleration of gravity is in the direction of motion. Its acceleration of gravity is downwards, which is the direction of motion. And so that's why it speeds up. And actually, even at that instant, at the very highest point, where it was going up and it's then going to be going down, the acceleration of gravity is downwards. It's changing its direction. So although when you throw an object in the air and it falls back, the velocity is changing all the time. It's up, it's then down, it's large, then small, then 0, then small, then large. The acceleration underlying that is super, super simple. It's always the constant acceleration of gravity. And so that was the motive for that particular quiz question. Okay, I'm going to get back to the lecture slides, and then we'll look at some numerical examples. Okay, so here we're moving to just working on numerical examples involving motion, involving equations of motion. So here's a question. So I looked this up actually in Guinness Book of Records. I don't know actually whether Guinness Book of Records is still published, but when I was growing up, I got one every year for my birthday. And Guinness Book of Records has all these facts about the largest this, or the smallest that, or the fastest whatever. And the world record for the longest skid marks on a public road, as listed in the Guinness Book of Records, is 290 meters. And it was by a Jaguar Mark II, apparently, approaching a traffic jam on a road called, I grew up by this road, that's why I put it in here, M1 motorway just outside London. And so that's 290 meters is the world record distance for a skid mark on a public road. And the question is, the police figured out how far the car was traveling before it locked its brakes and started skidding. And that's what we're going to do. We're going to figure out the initial speed of the car based on this information. And in doing that calculation, the police assume a known sort of measured average value for the acceleration when you skid, or the deceleration when you skid. And we're going to use that value. We're going to use this value that's in the problem of -6 meters per second squared for the deceleration of the car. And so we want to figure out how fast it's going. I mean, does the driver get a speeding ticket or not? And we're going to figure it from the length of the skid marks. And actually, you know, insurance agencies do this all the time. Based on the skid marks of an accident, they'll figure out how fast this or that car was going before the accident and know, you know, whether that car was or was not speeding. Okay, so here's my calculation. So the first thing I would always do in a calculation is make a little sketch. And so this red line here is where I sketched the motion of the car. So it starts out over here on the left, it's traveling at some speed, and then it ends up over here on the right. It's stopped over here on the right. And there's some information we know about this motion that were given to us in words in the question, in the problem. And so I then listed that information on my little sketch. So the first thing we were told was that the distance traveled, the length of the skid marks, was 290 meters. So that's the difference between the car's initial and final positions. X is the final position, X naught is the initial position. That difference is 290 meters. Another thing we know is that the car comes to rest. So at the end of the skid mark, the car was stationary. And so I wrote down the final velocity for this trip of the car is 0. And then we were finally told that the British police used -6 meters per second squared as the deceleration of a skidding car on a dry road. And so I wrote that down too. So these are 3 pieces of information that we know about the car's journey from left to right in the picture. And we want to figure out the initial velocity. And so we want an equation of motion that we can apply or use to solve for the initial velocity. And if we glance back at the equations of motion, let me quickly do that. Here they are. We want to consider these equations of motion. We want to think about what we want to figure out, which is the initial velocity of the car. And we want to think about what we already know. What we already know is the final velocity of the car, the acceleration of the car, and the displacement of the car. And if you think those things in the context of these three equations of motion, you can probably see that this third one here, it contains the quantity that we want. So that's important, obviously, V naught. And the other things inside it, the displacement, the final velocity, acceleration, we know. And so this equation in this particular problem, where we want this particular quantity, V naught, will work for us. Okay, so that's why I picked that equation. This little guy here, oh, sorry. This is our starting point, our choice of equation of motion. And so then I really went about applying it to this particular situation. This equation of motion becomes much simpler in two particular cases. One case, which we're going to use here, is if the final velocity is 0, this equation gets simpler, because this piece on the left-hand side will go away. And the other case it can get simpler is if the initial velocity is 0, like when we dropped objects from at rest, in which case this V naught squared goes away. So the equation gets simpler. So this equation is like the sort of the parent of two simpler special case equations, either when an object stops, comes to rest, or when an object starts from rest. They're both embedded in that, and other things too. Anyway, so I'm going to put in V equals 0, and we get this equation. If I rearrange the equation with the left-hand side being equal to 0. So I would move V naught squared from the right to the left, and then I would take the square root. And I get this simple result here, that the initial velocity, the thing that we want, is the square root of -2 times the product of the acceleration and the displacement. And the acceleration we know, and the displacement we know, and so we can feed them in. And so that's what I did down here. -2 times the acceleration, that's -6 meters per second squared, times the displacement, that's 290 meters. And I fed all those things in. And I end up with, for the numerical answer, needing to take the square root of 2 times 6, that's 12, times 290. And that comes out to be this 59 here, and the units of velocity, meters per second. Let me make a remark about signs in this particular problem. Signs of the different quantities, like velocities, like displacements, like accelerations in this particular problem. We said that in one-dimensional motion, we indicate the sign. We use the sign to indicate the direction. So in sort of motion, left-right motion, like this problem is the car traveling from left to right, will indicate whether this or that quantity, velocity, acceleration, is towards the left or towards the right with plus and minus signs. So I made a choice, and I called going towards the right as the positive direction, going towards the left as the negative direction. So you'll note that acceleration, which is opposite the motion, this deceleration, is negative. You'll note that the displacement which is towards the right, that's positive. And that was important. That was important because look at this equation, minus 2a times the displacement. If that quantity in the square root was to come out to be a negative quantity, you can't take the square root of a negative quantity. It must be, for this to be a valid equation, that that quantity inside the square root is a positive quantity. Then you can take its square root. And the way it became a positive quantity is, well, we have a minus in the equation, which looks dangerous, but then we picked up a minus here from the acceleration. And so we had a positive quantity in the square root. And so we get this answer, 59 meters per second. I did one last thing because I wanted to see whether the guy's getting a speeding ticket from the British police. Speed limit on a motorway, which is a freeway, is 70 miles per hour in Britain. So I took the 59 meters per second, and I'm going to convert the meters to miles, and I'm going to convert the seconds to hours. And I multiplied it by the relevant conversion factors. 1 mile is 1,609 meters. So this will change the meters into miles. This meters here will cancel with this meters here. And this conversion factor, there are 3,600 seconds in an hour. This will change the units of seconds into hours. So it'll get rid of the seconds here, and we'll end up with miles per hour. And if you do that, is 132 miles an hour. So he or she wasn't just breaking the speed limit. It was almost twice the speed of the speed limit. Okay. Let's look at another example. And again, this is an example of equations of motion, applying equations of motion to constant acceleration motion. And here's the question. So a ball is thrown into the air, and then it falls back to ground. And we're told that the ball is actually thrown vertically upwards with initial speed of 10 meters per second. And we're told an important thing, actually, and something we talked about earlier on, that we're going to ignore air resistance. So again, we can solve these problems with gravity's constant acceleration only if we ignore what are generally the small effects of air resistance. If we were to include the small effects of air resistance, these problems would become much more complicated problems that we wouldn't be in a position to solve. So we're always going to be ignoring air resistance in solving objects of problems involving dropped objects, thrown objects, kicked objects. Anyway, the question asks us to figure out, given the object was thrown up with 10 meters per second squared speed, 10 meters per second speed, how high does it get? And how long does it take to reach the highest point? Those are the first two questions. So how high, how long? And then there's a second pair of questions. I'll leave these for a bit later. How long does the ball take to fall back to the ground from the highest point? And what speed does it have when it strikes the ground when falling back from the highest point? But to begin with, we're just going to focus on the first two. If I can, these two questions here. How long and how high? Okay, so again, the way I would solve these problems is to make a drawing, make a sketch of what's going on. And I did this over here on the right-hand side. Here's the ball rising into the air from where it's released to where its highest point is. And I added to the sketch all the things I know. So I'm going to say that the object was released from ground level down here. So the initial position is 0. And the object was released with a speed of 10 meters per second. We were told that. I know at the highest point, that's where the speed is momentarily 0, because it's neither going up or down at that point. And I know that the acceleration is the acceleration of gravity. It's downwards minus 9.8 meters per second squared. And I want to figure out, I added this too, both the time taken for the trip and the, oops, there shouldn't be a note on this, typo, the final position, the maximum height of the ball. So we're going to figure out these two things. And again, I'm going to use the equations of motion. So the drawing, I think, the sketch, I think, is really important in sort of framing the problem and making it clear what you know, what you don't know. I think is really helpful, really useful to make the sketch. Okay, so let's figure out how long it takes to get to the highest point. For that, I'm going to use this equation of motion. Final velocity equals initial velocity plus AT, acceleration times time. I'm going to apply it to my particular situation. My particular situation at the final velocity is 0. So again, this more complicated equation gives us a simpler equation when you've got this special case of the object is stopped at the final moment, just like the car was stopped at the final moment. So that's going to go to 0, and so I can rearrange that equation for the thing that I want, the time, in terms of the acceleration and the velocity, initial velocity that I knew. And so I did that here. The time is minus v0 over a. And then I just filled in the initial velocity, divided it by the elapsed time, and I got just over 1 second. That's my final result. I did the same sort of procedure with equations of motion and solving equations of motion for the height that the object rose to. That's the position x. I picked an equation of motion that would work for me, that contains the thing that I want, that's the x, and the other things I know, acceleration I know, time I know now, and initial velocity I know. And so I just need to fill in v0, t, and a on the right-hand side, and that will give me the final height over here on the left-hand side. So I did that. Here's v0, t, product of initial velocity and time. Here's 1/2 AT squared, 1/2 the acceleration times the time squared. And if you multiply out these two terms, add together these two terms, you end up with this solution of 5.1 meters. And so that's a second example of the equations of motion. I'll end there. You can take a look on the next slide. It solves the last two parts of the problem, but it does it without doing any mathematics. It just works it by basic idea that the falling motion of the object when it falls back to Earth is just the reverse, the mirror of the rising motion as it climbed to its highest point. So the speed that it returns to the Earth with is the same as the speed it was released with. For example, the time that it takes to fall is the same as the time that it takes to rise. So you can take a look at that on the next slide. I'm going to finish there then. I'm going to stay on the on Zoom if you've got questions, and I'll have to look back in the chat. I may have been, with changing all these screens, I've lost track of the chat. But basically, to summarize, we've talked about Galileo's discoveries on falling bodies, and that all objects fall with constant acceleration, the same constant acceleration. And then we've looked at equations of motion. One of them we met with Galileo, that x equals 1/2 AT squared, but we expanded that. And we looked at examples using those equations of motion of objects thrown into the air and falling back down, and cars stopping. And those are the two sort of most famous cases, examples I can think of physics problems involving constant acceleration motion.